Hi there. You should have a Q&A on the side here. You should have a Q&A on the side. And while I cannot hear you, you can go ahead and type questions in. Let's see what we have here. Just going to wait for a couple of people to join here. Who do we have on the line? Let's see, I've got two people. They are missing what's going to be a very handy review session. Are you having trouble getting on? I'm just going to mail out the link here. Just give me a moment while I link to broadcast tonight. Here we go. Let's see, who do I have? Did you have any trouble getting on, the one person that's there? You can use the... All right. Well, for those of you on, let's go ahead and get started. What I'd like to do is I'm going to go ahead and share screen for a moment here. And it's a little bit of what we've been seeing before. And you should be able to see the general collections there. One of the things, as I mentioned in class, that I think is very useful to do is to set up a map for each of the key data structures, the interfaces, and then the implementers of them. And so basically one sheet for each one is handy so that you sort of have a map of that. As I indicated in the email, you can bring in a single sheet for notes, just a single 8x11 sheet for notes. You'll want to know the interfaces and their implementation so that thinking about for a particular interface, remember you design to the interface, what it is that you want them to do, and then we make a selection of the data structure implementation based on its attributes, typically for performance reasons, of which one of those two we actually choose. So nominally in your declaration, you will say that your variable is of type list or queue or map, and then we instantiate it with a particular implementation type. And so that is handy to know there. In particular, I think you'll want to know list and queue and set and map, but you should be also familiar with the others as well. The other thing you're going to want to remember is the distinction between iterable, meaning the collections are iterable, and that they support the interface for the one behavior called iterator, and that behavior returns an instance of an iterator, of the iterator class, and those instances are specific to those types of collections. And for example, we also have list iterators, and that they know how to iterate that particular type of collection. So remember, iterable, all collections are iterable. They respond to the message request iterator, and they return an instance of an iterator. So that's important to know. Array list and linked list are two list types, and you'll want to be familiar with their big O performance, as we saw in there. And in particular, think about the exceptions that occur for that. And you should have a good idea of the basic interface for array list, which is not only the get, but set as well, and then add, and add first and add last, and what happens when you add and remove those items. Let's see, I just want to go on to the next one. Array list, it's pretty straightforward. One of the things you'll want to know how to do with array lists and linked lists is be able to manipulate subsets of them. And we did those in the homework. We did them in quizzes, and you also had to do them in some of the labs, which is if I ask you to take off just the first and the last of a list, if I ask you to take off the middle item or the middle items of a list, all of those kinds of operations where you're thinking about taking a first and a last, or 0 and n-1, those two items, be comfortable with the notion of being able to index them and modify them. Likewise, with a linked list, you'll want to know the implementation of it. In particular, that they employ nodes to hold the individual elements in the linked list, and that each node in the typical linked list implementation has both a forward and a backward link. Also, imagine drawing the linked list itself, and you'll want to remember that linked lists have a pointer to the beginning and a pointer to the tail. In other words, there's two elements there. In the instance of a linked list, they point to the head and to the tail. If the list is empty, then clearly the head will be equal to null, and so will the tail be equal to null. However, if there's only a single item in the list, both will be non-null, but they could be equal to each other. So to test for an empty list, it's not simply adequate to test to see if the head is equal to the tail. It has to be, they both have to be null. Linked list performance, we want to think about the expected case for finding things in a linked list, and then worst case situations. And remember that both array list and linked list are both implementations of the list interface. So again, make sure you know that distinction. When we insert things in lists, it's relatively inexpensive once we get there. So if I have to get to some position in the list, that's going to force me to step over each item until I get there, and then I can do the insertion. Remember that that's why we use iterators, which is if I'm going to do something on each item in the list, I don't want to use get, because get starts at the beginning and wanders to the ith element each time. So I'd rather use the iterator, and we saw how that worked in the labs. You'll want to know shallow versus deep copy. In particular, what happens in a shallow copy? I only copy the values of the attributes, the actual values of them. I don't, if it's a pointer to something else, I only copy that pointer. I don't copy what it points to. That means if I really want what it's pointing to, I have to do a deep copy. Now, one thing you're going to want to have a good feel for is the binary trees. I'm just going to turn my question and answer off here. There we go. The question is the exam written or online? It is written, so you'll want to be sure to bring a pencil. We talked about that in class the other day. It is written as opposed to our online ones. So be sure to bring a couple of writing instruments, and you can bring a one-page sheet of notes that you can prepare that may or may not help you out. For binary trees, remember that not all binary trees are binary search trees. So if I construct a binary tree, it may not be in order. It may be, for example, our expression trees were set up in the order in which they were scanned in. Family trees, the order in which people were born, for example. But typically with our binary trees, we saw, for example, situations where if I add some items in to a binary search tree, and the binary search tree is not balanced, I can create some worst case scenarios. For example, in a binary search tree, in other words, where items that are less than the node go to the left, items which are greater than go to the right, based on what? On compare to. So everything that's in a binary search tree has to be comparable, so it has to implement the comparable interface. With the binary search trees, then it is possible to have some worst case scenarios, and we saw that where we inserted things in order. We also saw things where we inserted them in reverse order, and we wound up with a binary tree that deteriorated to a linked list. And that's why we want balanced trees. However, you should know how to deal with a non-balanced binary tree and how insertion and removal work in that binary search tree. You'll want to know pre and in and post order traversal. Recall that pre-order means that you're going to visit the node first, then the left, then the right. In order means visit the left, then the node, then the right. And post means visit the left, the right, and then the node. So the pre, in, and post all refer to where the node shows up. With maps and sets, In particular, maps, you'll want to know the two different implementations of maps. And remember that they are maps of key and value pairs, and that the key is what the map is indexed on, and the value is what's returned when you go to find it. So a good thing to have would be to know the key interface methods, the key methods of the map class, including the constructor, and then the accessors, and what happens when you do a put with a key that's already there and the new value, it will overwrite that value. And you saw that in both the dictionary and the DNS simulator. So if you are comfortable with that, then you should be okay with it. For hash tables, definitely want to know both the chained and the open addressing style, and how collisions are resolved in chained hash tables. There's a question here, are the slides on Blackboard? And yes, they should be. I'm just going to make sure I put them up. But I will also put them under the exam. And they are also under a lecture. Give me 2 seconds here, and I will add that in. There we go. So that is also up under exams, and the final review slides are up there. That you should be able to see now. With chained hash tables, you'll want to know where things wind up when you insert them, and they're also how collisions are handled. The other thing you'll want to know is about load factors and how those are calculated. So thinking about load factors, you'll take the number of items that are in the hash table and divide that by the size of the hash table itself. So if, for example, I have 18 items in the hash table, and it is a chained hash table, if I have 18 items in the hash table and I have 12 slots, 0 through 11, then my load factor would be 18 over 12, or 1.5. We talked about what happens as load factors go up. The performance of the hash table starts to degrade. We saw with open addressing hash tables that they degrade more quickly. And in fact, once they get past about 0.7, 0.75, they get dramatically worse, because you have to do more searching to find an open spot before you can insert something. And when you remove items, they're relatively expensive, but you don't need to know about removing items from an open addressing hash table. So you'll want to be able to calculate load factor on a hash table. With balanced trees, both AVL and red-black trees, you'll want to understand the key concept of rotation that we went over quite a bit in class. I hope not too much, but that you should understand a left rotation or a right rotation. And if I ask you to rotate something right about a particular node, what it looks like, or left about that node. Now, you'll want to also remember that AVL trees are as balanced as they can be, and they can potentially be off by one on one or the other sides, whereas red-black trees can be potentially off by two or more, but usually two. See, I'm just going to go back to this in a moment here. One second. Just have to make a quick adjustment. There we go. There. Sorry about that. Let me just go back to this for a moment. And do a quick screen sharing. There we go. Let's see. With red-black trees, you'll want to know the 4 different criteria for red-black trees and when we rotate things. And let's see. Just trying to think if there's anything else that is a let's see. I'm just looking at a couple of notes here. We talked about adding things into the binary tree, binary search tree. You'll recall that a binary search tree keeps things in order, right? That when we are looking at a binary search tree, and I was just going to open up binary search tree discussion. Just you should be able to see this here in a moment. With the binary search tree, we have a binary tree which has the root node, and it may be null, very important to remember. And then there's the left subtree and the right subtree. And then for binary search trees, oops, that's still shown properly. There we go. Binary search trees, we have the notion that, why is this doing this? There we go. Shoot. With the binary search tree, it is a subclass of the binary tree, and it enforces the, when we add things, it makes sure that it goes down the left subtree or the right subtree. In other words, it actually enforces the organization of it. It also knows that when it's checking to see something is in there, or when it's trying to find something, that it knows whether to go down the left subtree or the right subtree. So the additional constraint that it's putting on the binary tree is that it's actually ordered. And so the for binary search trees, it does have to have items which are comparable in them. In other words, they respond to the comparable interface. Let's see. I'm just looking through my notes here, see what else I think is really important. When we looked at unbalanced binary search trees, meaning that we did not do the rotations, we knew that it was possible for those to get a little bit out of hand. And so when we add things into that tree, it is possible, we're always going to have to search down to the node unless we find it. And so we're always going to have to search down to a leaf, and that leaf may look like a linked list. So it's not going to have log2 of n performance. Oh, recursion. Let's just talk about recursion for a moment. 3 good exercises that you can do tonight for recursion would be to find the height of a tree and to find the number of items in the tree using recursion. And let's see, I'm going to just open up my slides on recursion here. There we go. For recursion, I'm just going to share these slides. Here's a couple that we can do. One is we saw the reversing the order of a list, where the base case is an empty list. The recursive case is doing the reverse of the remainder of the list and then adding on the first item of the list. And we saw how to do that. the there's, for example, for height, and you know what I'm going to do? I'm going to add that in. I'm going to add a slide in here. And then share that with you. For the height of a tree, if the root is null, that means that the height is 0, so we return 0. Otherwise, if the root is not null, then we return 1 plus the height of the subtree. Wait, do we do the left subtree or the right subtree? We find the maximum, whichever one's larger, the maximum of the height of the left subtree and the right subtree. So we're going to find the max of that. And we call it recursively on the left and the right. So we take, which turns out to be, so that if the left one has 3 and the right subtree has 4, then we'll return 1 plus 4 and return that up. Now eventually it'll get down to 0, and it'll return 0, and then 1 plus that, and 1 plus that, all the way up. So that's a good one to know. The other one that was good to know would be size. And we saw how to do that. If the root is null, that means the size is 0. That's easy enough. Otherwise, the size of the tree is 1 plus the size of the left subtree plus the size of the right subtree. So if there's only one node in it, then it would be 1 plus the size of the left subtree, but the left subtree would be null, and the right subtree would be null, which would both return 0, so it would be 1. Otherwise, we continue down the tree. So you'll see here that in the bold is the base case, and then this one, which we'll put in red, for example, is the recursive case or the recursive step, and we make the problem smaller by taking the left subtree and the right subtree, both of which are smaller than the tree itself. Okay. I think we're just about done here. We talked about hash tables. Oh, one other thing in hash tables that I just want to refresh our memory on, and that is go back and share this. With hash tables, We know that with open addressing, if the size of the table is n, and it's indexed from 0 to n minus 1, then the most items we can have in the hash table is n. In other words, the load factor can never be greater than 1. However, with chained hash table, we don't really have any limit when it comes to collisions. So if I have a hash table that's of, say, size 7, and I put 21 things in it, if it's completely even, in other words, if it just so happens that exactly 3 items are hashed to each location, I have my load factor of 3, and it's as efficient as it can be. However, worst case scenario, if they all happen to hash to the same location, let's call it 5, then I would have a linked list of 21 hanging off that one location, and that would be the most degraded performance possible. So if I have a bad hash function, then in that hash, then such that they all hash to the same location, then I'm going to have a very degraded performance. So, quick little summary. Know your Java collection framework. Again, I would sketch it out. That's handy to know. Know the basic operations of list, add, remove, contains, adding and accessing location 0 and the tail. Know the difference between shallow and deep copy and how we handle that. Know the distinction between binary trees and binary search trees. What's the difference between those two? And what is that additional imposition? The fact that it's ordered. And that means that all of the items in it have to respond to compare to, meaning they implement the interface comparable. Know about the fact that maps have keys and values, and that the that search is based on the key and it returns the values in maps. The load factors in hash tables, and then finally the concepts of rotate left and rotate right in the balanced trees. And then, of course, we went through a bunch of examples of what were reasonable implementations for different design decisions, and you might want to go back and take a quick look at those. And that's about it. I can't think of anything else. If you feel comfortable with that, let's see. There. If you feel comfortable with that, then you should be in pretty good shape. Any other questions before we wrap up? We only had 3 out of 21 people attend. They're going to be sad they missed this. Number 1, make sure you bring a pencil or pen. I'd recommend pencils unless you're like super certain of what you're doing. Eat something before you come, like some protein, etc. Don't eat a donut right before you come in. And bring your 8.5 by 11 sheet of notes if you'd like. You don't need to, but it can be handy when it comes to some of the framework stuff and some of the interfaces. So I will see you tomorrow morning at 11 o'clock in room CC210. You should know what makes a good hashing function, but you don't need to be, to actually write one. Can the notes be typed or handwritten? They can be typed. I would have to type. I have bad handwriting, as you've seen in class. Good question, though. All right, gentlemen or ladies. I don't know if Ms. Dora's on the line here, but we'll see you tomorrow morning, CC 210, 11 a.m. to 1 p.m. Have a great evening. We'll see you later.